Okay, has anyone seen these flyers around or gotten an email about this? Anyone planning on going to this? Guess where it is? Right here. Guess what time? No, it's actually after class, but it's like an hour after class. It's at 7 p.m. tonight. Technically, you should have RSVP'd for it, but I heard that there's plenty of seats now. So if you want, this is about, I used to say turning. That's actually wrong. It's Turing, T-U-R-I-N-G. It's a film about Alan Turing, who's a giant, or was a giant in the computer science field. Did a lot of work in World War II to break like Nazi codes and things. If you ever heard of the Enigma machine, he had something to do with that. In fact, I believe that's an Enigma machine up there. And the actual creator of the movie is going to be actually screening it. So if you want, stop by there. I'll be there. It should be fun. Should be a good time. OK. I'll put that up again at the end if you want to. There we go. OK, so here's what we're going to do today. We are going to be talking about some esoteric data structures. Well, we may only get to one, maybe two today because of some other things we're going to do first. But we'll get to some data structures that you might not have seen or you might not see in any other classes or unless you're like digging in deep to some things. But some of these are used very often, and they're actually kind of cool. And in fact, the one that we're definitely going to see today, we will actually get a chance to do a little bit of calculus based to do this thing. So it's probably also the only time in a computer science class where you'll ever do any calculus. And it's also like this much calculus, right? It's like something that is not hard, but it's still calculus. So hey, we'll call that a win. All right. So what we're going to do before we go into that is we're actually going to talk. I'm going to go into a little more detail about this song search project. Is anybody still like, holy smokes, this is a huge project and I don't even know where to start? Yeah, a few people are like that, right? Here's what we'll do. We'll walk through kind of the big ideas and talk about some of the data structures that you can use for your project. You do not have to. These are only suggestions. If you think you have a better idea, awesome. Use whatever you want. I'm just going to give you some suggestions for those of you who are kind of like, I don't really get what's going on. OK? And I also will give you, I will talk to you about how to use this thing called a vector, which is basically a dynamic array where you get all the hard part for free, the expanding and all that kind of stuff. OK? So that's what we'll talk about. Any questions before we get going? Denise?
Hard part for free in terms of like the work or in terms of the memory and processing?
In terms of like, you don't have to expand the array. You just put stuff into it, and it's like, oh, I need to expand, and it does it all on its own. So. It's the expand part that's really the hard part. It's like you just keep putting stuff into it, and it says, how big am I? Oh, I need to expand it. It does it all in the background for you. You'll see. I'll show you.
Does it do the same like new array thing and then copy it over?
Yeah, it does. It does all that in the background for you. Yep.
In terms of processing and memory, it's still acceptable.
It's not going to be much better. Well, it'll probably be somewhat better than the one you might be able to write just because they've tweaked it to make sure that it's like really efficient. But otherwise, it's exactly the same as the one you would do. So you can certainly use your own dynamic array. That's perfectly fine. But if you want one for free, because there might be a place where you use lots of them. And remember, with dynamic arrays that you create, the way we've been doing it, you have to come up with your own, you have to figure out how to put your own data structure into an array. This one will handle any type of data structure you want. I'll show you. You'll see. OK, any other questions on that? No? OK. All right, so let's talk a little bit about this song search thing and then some of the possible data structures. So we've got a lot going on in this project, right? There's a reason that document was like 9 pages long about how to do it, right? There's 117,000 songs, which means that you've got to be efficient, right? That's kind of the whole point of this is like, hey, have you learned anything about using efficient data structures so far? We have to store in some form or another, without losing any information, all the lyrics for each song, right? Why do we need to do that? What am I forcing you to do that makes you so you have to store all the lyrics? Context, right? You're going to have to print out the word, the 5 words before and after in the order that they come in and with punctuation. So, you have to store that. OK, so we better figure out how to do that. We'll talk about it in a second. You have to be able to search for a word that appears in songs. So when we talked about this already, if you're Google and you're searching Google, you want to be able to do it fast, and you want to be able to do your searches for the song search fast. So we've got to come up with some sort of fast data structure. What are our choices for relatively fast searching in data structure so far? Hash table's good. What else? Try's not bad. What else? A tree is pretty good. A tree's logarithmic, and that's fine. I think you can do this problem perfectly well with a tree. Might not be quite as fast in some cases, but a tree is perfectly fine, right? What other kind of specialized tree might we think about? What was it? A binary search tree, sure. You're going to want a binary search tree. What other kind of prefix tree? What do we call that? A trie. Trie's not a bad idea. Some people definitely use tries very effectively for this. And what other things can we do binary searches on? A heap? Not really. You can't really do a binary search on a heap. But an array, you could do a sorted array if you wanted to. It'd be a little crazy to do that, I think, for this assignment, but you could. OK, so there's lots of different ideas. OK, but we'll come up with some, and I'll show you one that I might think about using. OK, so you got to do that. All right. And then we have to rank the songs based on how often a lyric appears. So if you have a song and you're looking for hello, and hello appears 1,000 times in that song, and that's the most, then that song needs to come first with all those 1,000 times underneath it. So when we talk about ranking, what are we really talking about? What is it? Yeah, I mean, I hear it over here. Yeah, relevance is good, but in order to get the best relevance, we have to do what? We have to sort things, right? So you're going to have some sorting going on here too, and we'll talk about maybe some of the best sorts you can use for that. By the way, the people that I've graded so far for the homework 4, or rather homework 5, great job. So you guys, I think you guys get sorts at this point. Okay? All right. Questions on any of those? We're going to talk about those in detail in a second. Okay? All right. So there's 117,000 songs, right? OK, let's step back a second and talk about what a song, like what structure should a song be? What's a good idea? A struct? Struct could work. What else? A song class. I like that a little better, only because C++, well, structs and classes are really the same thing under the covers in C++. But we generally want to think about it in terms of a class. You'd probably want to do that. But if you want to make it a struct, fine with me. It doesn't matter. It's pretty much the same thing. Yeah? I don't think a struct has any, or a class has any extra overhead than a struct. Not in C++. In C, structs are much lower level. Like there's less going on. But in C++, structs are really classes. They're the same thing. Everything under the covers is like literally the same. Why is there more in C++ to a struct? Because they're allowed to have functions basically embedded in them, just like a class. Yeah. OK. So Mackenzie, what's up?
Did you say structs can have a function?
Structs can have functions in them. Yeah. Yep. Yeah. Here's the difference between a struct and a class. The only difference, as far as I know, the only difference is that a struct, all the functions are by default public, and all the members are public. Whereas in a class, all the members are by default private. That's the only difference. So otherwise, they're exactly the same thing. But yeah, so you can use a class or a struct. But what are we going to put in this song class? What kind of information would we put in there? For each song, what are we going to put? Alice?
The author.
Author, which is going to be what kind of type?
String.
Yeah, like a string, right? std. If this is in the H file, we're not going to have the using namespace probably. So std string, right? And that's going to be the author. What else? Title. Same thing. std string title. OK, what else might we need in there? Yeah, the lyrics, right? And what are we going to put the lyrics in? Yeah, what do you think? Yeah, okay, so for now, let's just call it an array, right? An array of strings. And we will turn that into this thing called a vector in a second. And that's going to be the lyrics, right? OK, anything else that needs to get definitely go in here? Yeah. You have to return the punctuation exactly as it is, yeah. 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 That's hopefully not hard to do. If you're storing all the lyrics, you're storing the lyrics. Like when you store, you know, hello, exclamation point, you're going to store all of that as one word. Right? When you store WE apostrophe RE, that whole thing is going to be the word. WER apostrophe comma, that whole thing is going to be the word you're storing. This comes out of the algorithm as the word. OK? We're going to take care of this punctuation in our searching later. But for now, just you're going to store it that way. OK, who else saw, what else do you think should go in this song? Anything else? Yeah, what do you think? The number of words in the whole like song, number of lyrics? Well, yeah, you know what? That's going to be part of the array. So yeah, you're right. We would want to keep that. We would want, if we were just doing an array, we would also have to keep that separate. But guess what? The vector will do that for us. So we don't actually need to keep that separate. Good idea, though. OK? Yeah? The duration? You know, for a bigger database that has that sort of stuff, sure. We don't have that information. So yeah, good idea. But yeah, what do you think, Julia? So this is a good idea. Word count that you're searching for. I don't think that needs to be part of the song, because that's going to come later, right? And you're going to store that part in a different database. Now you could, if you wanted to, you could probably have like a frequency table in here that lists all the words and all their frequencies. That's actually fine if you really wanted to. The problem is being able to search into the song is going to be a little harder that way. So we probably want to make that a separate thing. But good idea. But I like that. But maybe we want something like an insert lyric or something like that. String, lyric, something like that. Like a function that actually inserts the lyric, something like that, right? Void, maybe, you know, whatever. But maybe some other functions. But for the most part, I like what we've got here. OK? There we go. That's terrible. Hold on. There we go. I'll do it the other way. There we go. So, and semicolon. So yeah, so I think this is a good start for a song class. Now this is where you're going to keep all your songs. Song class, we've got what we did. What data structure should be used to keep all the songs? Jade? Another dynamic array, right? So you're going to have a dynamic array of songs, right? Each song is going to go into this other dynamic array, right? Which is going to have the potential to do that. Now, you don't have to do this, right? You don't have to keep some other thing. But what's nice if you do this is at the end, when your program ends, you just walk through this whole list, delete all the songs, and you've cleaned up your memory, right? So that's nice if you do it that way. And you've also got a nice index value if you want to keep an index value of where in the array your song is. So that's nice too. You could keep pointers to the songs, which is perfectly fine. But if you keep an index, it's more or less the same idea. OK? OK, so far so good? Song? All right. We're going to keep this dynamic array of vectors. OK, so I keep mentioning this thing called a vector. I might as well talk about what it is. This vector is just a dynamic array. Under the covers, it's very similar to the dynamic arrays that we have created before, right? It's an array that it uses new to create the array. And then when it needs to expand, it creates a double-sized array and then copies of the elements. But it does all that for us, right? And what's nice is you still use the bracket notation. In other words, if you have your songs, you can still say songs bracket 4, which gives you the fifth element in the song, the fifth song in that array. You can still use that. It's just they just overload the bracket for a vector, which is great. Okay? You can also get the size by, it's a method that you just call on it. So you would say songs dot size, and then that would give you the actual length of the array, which is nice. Okay, so it's got all that built into it. All right, and you don't have to worry about any type of expanding or worrying about keeping track of the size. It does it all for you. Okay, so we do that. It's also got this interesting thing called an iterator. Now, if you've ever used Java, you probably know a little bit about iterators. But if you haven't, I'll show you what that is. You don't have to worry about this. And if you're like, oh my gosh, my brain is full of C++, I don't want to learn anymore, you don't need to learn this, right? But if you do want to learn it, it's actually kind of a clever way of walking through a list. Okay? And you will see the iterator pattern in many more languages as you go along. Okay? All right. So what does this actually look like? Here's the very small. Let me see if I can bump this up. There we go. There we go. OK. So for I'm trying to find a better piece of chalk. I keep forgetting to get more chalk. And these tiny little pieces don't work so well. There we go. Well, better. OK, so in here, first things first, you need to include the vector. Right? So you need to do that because that's the header file for this. In fact, I believe I highlighted it. There we go. OK. All right. What you also have to do is you have to say, look, here's the type. We did something very similar when we used queues and stacks before. OK. What you do is you say vector, and then you say what you want to put in the vector. That can be anything you want. It can be your song class. It can be a string. It can be an int. It can be whatever you want, which is cool, which is really nice about this idea is that vectors will take anything, and they'll be able to figure it out. Be able to deal with strings or songs or whatever. In this case, you put what's going to be in, and then you do the name, semicolon. It does all the other details about creating it and whatever behind the scenes. Okay? And then you can actually store them. What I've done is I've actually come up with a regular array to then copy this into the vector just to show you what's going on. Question? Somebody have a question? No? Thought somebody had a hand up. OK. So I've created another array. Right? Mary had a little lamb. We had this big discussion earlier today whether it's its or whose. Which one is it? Is it whose? All right. Anyway, whose fleece was white as snow. OK. And what I'm doing in here, this is just copying it into the list, and you move something into the dynamic or into the vector with this statement called push back, and it's just saying push it onto the end of the vector. And if the vector's not big enough yet, it will expand on its own. So you just go through and just go push, 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 and they're all on there. Okay, which is kind of cool. And it's really the same thing under the covers. Yeah. No, it would just say song, right? Because it's an uppercase song in this case, because we made a class called song. That make sense? OK. So that's how that would work. So anyway, just go through it like that. Now, this is where it gets to be a little bit fun and more interesting. Let's do this. Maybe a little bit bigger. Whoops, too far. Oh, I have no mouse cursor, so I can't really see where it's going here. Anyway, there you go. OK, so here's what we're going to do here. We can print it out using two different methods. This should look very familiar, except for maybe the size t. All that means is an integer. Just use that as when you use the size method, you get something that's in a size t integer. Just use size t, you'll be happier. If you use int, it probably won't break. It might give you a warning, but it won't break. But anyway, it's just an int. And then you say for size t I, that's saying I'm using my variable I. I is less than the size you just came up with, plus plus I, or I plus plus, doesn't matter. And then you print it out, string list bracket I. That should look very familiar. Right? You've probably seen that 1,000 times before. Okay? That's one way to do it. The other way is this very interesting thing called an iterator. Okay? An iterator is like a behind-the-scenes ability to walk through anything. What you can do is you can say another type, and the type is an iterator type of the class vector string. Right? The iterator, that's the definition for I. And what you do is you say I equals the beginning of the string. and then you loop until I, or while I is not equal to the end of the string. Okay, it's like making it more generic, right? It's making it more generic, and then you do plus plus I. But here's where it gets interesting. What you then do is to print out your value, you actually say star I as if it was a pointer to the string. Right? So it's saying dereference I and print it out. And that will print Mary, then had, then a, then little, then lamb, etc. OK? That's what that is. And this iterator, somebody said this earlier in the other class. It was actually kind of clever. They said this iterator thing is like a hybrid between an integer and like a pointer. And it kind of is, in the sense that you can say plus plus I, and it goes to the next song in the array. Right? It's like the next song, next song, next song, just like it was an integer going 1, 1, 1, 1, 1, 1, 1. But it's also pointing to the actual place in the array. Okay? Like I said, you don't have to learn this if you don't want to, but it's another this is more of a C++ way of iterating, of going through a list. Yeah?
This is also a next function if you don't want to use it like an
If you don't want to do which?
You can do like, if you don't want to use it like an int, you can use like an i.next.
Oh, there is a next. I think there probably is a next function, yeah, as well. But anyway, either way is fine. If you want to learn this way, it's a little more C++-like, but this way works perfectly fine for vectors. So either one is perfectly OK. OK, questions on how on using vectors? Yeah?
What's the point of the iterator?
The point of the iterator is to make things more generic. So you can plop this exact same code into some other function. The only thing you'd have to change is the type over here, and it still will work exactly the same. So it's like you would see this much more often than you'd see something specific like this. That's really the big difference. And it's also a little safer in the sense that in this case, you could end up walking off the list if you changed I or whatever. I mean, you can change I down here, but it's going to give you an error instead of like segfaulting probably. Although it might segfault because of the error, but different story altogether. OK, so it's a little safer in that sense. More C++-like, part of the language. That's the way it goes. OK. All right, so any other questions on the vector? If you have trouble figuring out how to use it, go back to this slide and take a look. And it's all right on here. And I've highlighted all the parts that you need to pay attention to. OK? Remember, it's just like a regular array. Bracket notation works fine. OK? Anybody else? OK. All right, so we've got the how to store the songs, right? We already kind of talked about this. We're also going to store the lyrics in another vector. That's a good idea. You don't have to. If you want to come up with some other fancy way of storing it, fine with me. But that's not a bad idea, to put the lyrics in another vector per song. OK. All right. Now, talking about search. OK. Have I talked to anybody in here about their actual project yet? I forget. A couple people I did. I always ask the question when I'm talking to you, and you guys can see me or see a TA. Hopefully they'll ask you, how do you do the search? Once the database is in there, walk me through the search. OK, and that's the part that a lot of people are like, I guess it's going to do this, and then I'm not sure. Right? And you got to know that before you actually build this. OK, so how are we going to actually look through the search? OK, first things first. We have to make sure it's an alpha-only word, because that's what we're searching for. Right? I gave you a function that's called alpha-only that will turn a word like, let's say you have a word like B-E-G-I-N, comma. I don't know why it would be that word, but let's say it was that word, right? B-I-G-I-N, comma. What that turns into is lowercase b, E-G-I-N, and that's it. OK, so if you're searching for lowercase begin, or if you search for uppercase begin, it will turn into this and do the search on the lowercase version of it. OK, and you have to return values that match the full version as well. OK, so we'll get into the details. If you have questions about that, we can get into the details about how to do that as well. OK. So we have to do that. So the alpha only function works to do that. And by the way, it's not alpha only. I kind of lied on the function. It will turn A, B, C, 1, 2, 3, it will leave that the same. It will still be A, B, C, 1, 2, 3. If you had uppercase A, lowercase b, uppercase C, comma, 1, 2, colon 3, that would become A, B, C, 1, 2, 3. Make sense? If you're thinking of doing a try, be very careful because you have to account for the numbers as well. How many children could each value in a try have in our last version? 26. How many does it have to have now? 36. OK, so if you're going to use a try, keep that in mind. Okay? All right, so we need to do that alpha only. And then we need to store it in this data structure. What kind of data structure are we going to use? We had some ideas earlier. OK? We had some ideas earlier. We said there was a try, there's a hash table, there's a tree, there's some other things. But regardless of what you use, we have to figure out what to do once we find the word in that data structure. OK? So I'm going to erase this. And then we're going to write up here what we might do. All right. For whatever structure you have, let's call it a hash table for now. But again, you can use whatever you want. Let's say we look for the word hello. Right? We look for the word hello. And hello says, there's where it's going to be, right there. That's where, in whatever structure it is, it's right there. What is going to be in there? That's the big question you have to answer. Ideas. Yeah?
The word node.
A word, OK, a word node. What's a word node?
Or an array of different.
An array of word nodes?
Yeah.
What do you mean?
So like every time that you put one of the words from the songs as you build up your song,
Mm-hmm.
your list of songs, you can hash the word
OK.
where it would be put onto that table. So then you get an array of like words.
So OK, give me an example of what's in here.
Okay.
For hello, what's in there?
It'd be a bunch of hellos from every time hello appeared in the song.
What's different in the hello that's in Rick Astley versus the one that's in Michael Jackson?
It'd have like the artist and the title.
Oh, OK. So it's, but why do we need more hellos? We already know this is the hello box.
Because then you can keep track of how many times that hello appeared in the song.
OK, so Lionel Richie has a song that's like, hello, is it me you're looking for? And he says hello like 1,000 times in the song, right?
Yeah.
So you're going to have a different hello for each time in that song?
Yeah.
What's the problem with that?
No, one hello
No.
per song.
One hello.
Like a count.
OK, I guess I don't understand why you need another hello. You already know this is the hello box. Why do we need another hello?
To keep track of each hello from every song.
We don't need more hellos. We just need something that's keeping track from the song. This is the hello box. But I get what you're talking about. OK, so what's that structure going to look like that's inside here? I mean, I get what we can keep going down what you're talking about. What's the structure in here going to be?
Another array.
Another array. Why not? Yeah, Jade?
Could it be like a class of just the title and then a count of how many times?
Well, OK, but this is really this is the same thing. But we do need some other like array here that has that information in it, right? And I think both of you guys are getting to this. So this is the hellos from one song. This is the hellos from some other song. That's kind of what you were getting at, right? This is the hellos. Now, Jade, what were you saying? What needs to be in the hello? What needs to be in here?
The title of the song and then like a count of how many times that hello appeared.
OK, I like the count idea. So let's say 3 for the count. I'm not sure I like the idea that it's a title and an author, or a title and an artist. I like the idea that it's an index into what? The song array that you had, right? You have this big song array, song 1, song 2, song 3, index 0, 1, 2. And this is going to be like, yeah, so let's say this is the Lionel Richie song at index 1. It's going to be a little 1 and a 3. So this could be a struct or another class or something like that. And I like that. I like that a lot. Now, you said it's going to be for every song that has hello in it, right?
Yeah.
OK. What if it was the? How long would this array be? It might be up to 117,000 because that might be in every song. right? Right? Except for some rap song, it's like do 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 instead of the or whatever, right? You know, whatever. But it's like unless there's the in it or whatever, right? But the point is, yeah. So you might want to. I like that idea. At least to start out, that is a great idea. And this is another thing we should probably talk about. Breaking this problem down into chunks is going to be one of the harder things to do because you want to be able to test it as you go along, right? If you try to do the whole project at once, you're going to be like crazy. You're going to go nuts, right? So what you should probably do is break it down into pieces. Come up with your song class, right? Try to put try to put some lyrics into that song class, just straight off the top. Test that. Make sure that lyrics can go into that song, right? Then make an array of songs and put more songs into that, right? And at that point, you can actually start using like the read list thing to put those in there, okay? Then maybe hash some things, and I like the idea of keeping every song so far in this array, this vector. This is another vector maybe, right? This is another vector. And at first, do all the songs in there. Because for the Rick Astley database, which has like 9 songs in it, that's fine, right? This is going to be perfectly fine. Who cares how big this is, right? It's only 9 songs. Is this going to be tenable for the 117,000 songs? Probably not, because when you look at hello and it shows up in 40,000 songs, this array is going to be 40,000 long, and that's a long array. Do we need all 40,000? What do we need, Deanna? 10. This needs to be 10 songs long. Okay? Now there are various tricky ways of keeping that 10. In fact, let's talk about a couple of those. Okay? Let me start out. Let's pretend there's no hello in the database yet. Okay? We go to our first song, and the first song says, hello, I mean, hi. I don't know, whatever, right? So there, okay, and then there's a hello, right? And then somewhere else in the song it says, you know, hello to everyone, whatever, right? Okay, so there's a couple different hellos in there. Here's what happens. The read list function gives you the first hello, and it says that's by such and such author in a song. You put that song in your list. Then you have to deal with this hash table or whatever. Hello, you hash it. It says, OK, I'm going to go here, right? You have some vector here. Are there any songs in it yet? No. OK, so is our song at this point in the top 10? It is right now in the top 10. Song 1, or index 1, index 0, or whatever, right? How much is the count so far? 1. OK. Next word, I. Do the same thing for I. Do the same thing for mean. Do the same thing for hi. You get to hello again. It comes back here and it says, here it is. Oh, look, there's an array already. Is my song in that array? Don't you have to check that? Right? So you go through, you say, OK, is my song in that array? Right? If it is, or maybe you're also keeping a count over here. But for now, we're going to go and we're going to find out if song 1 is already in here, what are we going to do to this number? Make it 2. OK? OK, do you see how that works? Going forward, though, eventually this will be song 11, song 43, song 18, right? And it'll be 2, 7, 15, 12, 36, and 9. And it'll be full. The next song that comes by is going to come to hello, and it's going to go do what? It's going to come over here. The first hello. It's going to come over here, and it's going to see that my song's not in there. OK? Should my song be in there? Do we know yet? Right now you say no, but we don't know yet. This song could have 1,023 hellos in it. Right? It could be another rap song that goes hello, 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 right? Right? Who knows? Right? And it could be there could be 1,000 hellos in it, but we don't know yet. So you have to figure out how you're going to do that for all the letters. Here's a suggestion. This is something that we thought about last semester. It worked great. What if you kept an 11th song? And you put the new one in here. This is song 114. Hello by hello. Right? And you're going to you're going to put it in there, and it's going to be song 114. And what number are you going to put in here? 1, because that's all you've gotten to so far. Then you get to the next word, and it's hello. What do you do here? You make it 2, right? Now, at some point, right? At some point, this 2 is going to end up greater than one of the other top 10 songs. What does that mean about this song? It just became part of the top 10. What does that mean about the other one that is now less than this one? It got bumped from the top 10. Will that other song ever be in the top 10 now? No. So what you could do is you could swap it with the one that is the 11th song, the one that you just got to and figured out, hey, this is now the top song. If you do that, then when you're looking at your top 10 songs, just look at the top 10. This 11th song might be a song with only 1. It might be with 10. It might be with 4. Who cares? It's not in the top 10. Just print out, go to the top 10. So do you see how that works? That's actually one way to do it. There's other ways to do it too. You could keep it just a running total of the list. And I mean, there are other ways to do it. But I think that one would probably work OK. Yeah?
So the top array, I'm not sure, are you making this after you put everything in the program, or are you doing this while you're putting it in?
Good question. You can do a couple different things. You could read all the songs into your array. And then you could go back and you could go through all the songs again and put it into this thing. It's probably more efficient to do it as you go along, right? But if you think you have a better method, like let's say that in your song you want to keep a frequency table of all your words, right? And then you can actually go and put it all in the hash table or whatever later, fine. If you think test both if you want, you can see it doesn't matter. Whichever one you think is more efficient. Fine. Yeah.
We're just testing for words, right? Not phrases.
You are just testing for words, yes. So no phrases. A word you can test for a word 1, 2, 3. That should show up, right? But you can't. You can test for 1, 2, 3, comma, but we're only looking for 1, 2, 3. ABC, comma would be ABC, right? Yeah. OK. Are we done yet? No, we're just putting things in. How does a search work? Like that's like the next thing, right? That wasn't it. Did I do it there? Oh, I don't even think. Let's see. How does the actual search itself work? Like, how do we search? And this is the question I'm going to ask you when you come to me and say, here's my data structure. How does it work in this one? Max? OK. Almost. So I type in hello, exclamation point. OK, so you do alpha only on this word. Then you look for it in the hash table, and it tells you it's here. Then what? Go to the top 10 list if you're keeping a top 10 list. At first, it might not be a top 10 list, but OK, fine. You go into a top 10 list, and then what? You can keep it sorted. Doesn't yeah? You can keep it sorted. That's fine. But let's say it's sorted. That's fine. This is the one with the. This is the first one you're going to print out. What are you going to do? OK, so you go back to the original array. You get the title, get the artist. Then what do you do? Yeah, you figure out how to get. You have to figure out how to get context, right? Somebody want to walk me through getting the context? Somebody other than Max who's just answered. How are we going to get the context in a word? I'm looking for. In this phrase right here, I'm looking for all the hellos. How are we going to do it? Go ahead.
Keep the indices of where they appeared and then use the vector to go.
Oh, you could keep the indices where they appear. I bet that's going to be too much space. And here's the other thing. At this point, how many total songs do you have to look through? 10. Once you get down to 10, that's basically free, right? Like doing 10 songs is the free part of it, because it takes 0 time to go through 10 songs. So don't worry about having to go through this word by word. Like, don't try to maximize this part. Try to maximize getting to this part, which is the whole 10-song thing, right? Once you get through the 117,000 songs and you're down to 10, now you can be as slow as you want, really. Start here. OK, what are we going to check for? Is it hello? And it is. What are we going to print out for our context? The previous 5 words, which are none right now. Then you'd print hello. Then you'd do what? 1, 2, 3, 4, 5. You'd print those 5. Then is this the hello? Nope. Is this a hello? Nope. Is this a hello? Nope. Is this a hello? Yup. I'm going to print 1, 2, 3, 4, only 4 before, and then I'm going to print 1, 2, 3, however many are after. See how that works? You have to be able to do a loop to do that. And there's like corner cases in there, so you have to be a little bit careful. A little bit careful. Alice? It prints out with all the punctuation. No, there's no 2 alpha. But you're going to keep the, you're going to basically do for each one of these, it's going to be like a password hash a little bit. You're basically going to take for each one of these, you're going to say is what's the 2 alpha?
Yes.
Oh, that's what you mean for this one. 2 alpha hello, is it hello?
Yes.
2 alpha I, is it hello? 2 alpha me, yeah, that's what it is. Good. Yeah, Daniel.
So before we even search, we could create some sort of structure that pulls every word of
Yeah. Right, which you've done with a song class. You've done that for each song. It's going to keep a total, it's going to keep all the lyrics in its own little vector for every song. Yeah, is this going to take a lot of memory? Yeah, it's going to take a lot of memory, right? But we know that already. Right, we know it's going to take a lot of memory. Yeah. Alice?
So you said that we're supposed to do like a link to the actual database?
A link to the actual database. Oh, you mean for the, like a hard link to the, or a soft link to the, yeah, sure.
So isn't it going to be like the same, about the same amount of data storing it in here, or just broken down less, but it won't?
No, it's going to be the same amount.
Okay.
So the database is 200 megabytes, which means you're going to take at least 200 megabytes to store the database.
Okay.
Right? And then you've got to do a hash table, which is however much else memory you're going to take. But the database itself with just the lyrics is going to be 200 megabytes at least.
But that's
Yeah.
not part of our, that's not in our,
No, that's going to be in memory while the program's running.
then this search thing,
The search thing's also going to be in memory.
that's going to be smaller.
It's going to be smaller. Well, it should be smaller because
It's just the top.
it's just, well, first of all, it's just the top 10. But second of all, there's 100 million words in this document. But how many are like repeated? A lot, right? There's thes all over the place. There's whatever all over the place,
Yeah.
right? Yeah, Jared.
I'm just making sure I got something quite right. So
Uh-huh.
that square that you have below, you search for hello points to that.
Yeah.
So what points to like the other squares? Like what encompasses what the other ones are?
Yeah. So let's say you're searching for baloney. Baloney might hash here. Then it's going to be all the top 10 songs that have the word baloney in them.
So with so many words in the English language that
Yeah, this could be as right. This hash table is going to be as big as basically the words in the English language. Yeah, plus weird ones like faux shizzle and all that. Right? Right? Words that aren't in the English dictionary. There might be up to 1 million, let's say, 1 million unique words, probably. Yeah. So this table itself could be 1 million long, but really, I mean, that's not that much these days. But yeah, but I think you get it now. Yeah. Okay, other questions on this. So I think we've walked through the most of like an idea for it. You can come up with your own, like you have to come up with your own ideas on specifics, and you can certainly go outside the box. I'm happy to for you to go outside the box. But this should get you started on a good plan and like all the things you have to think about. Right? Okay. Danielle, what else? Danielle always smiles before she raises her hand, so I know she's going to raise her hand. She goes smile and then boop. Yeah.
Just like to clarify, when you say hash, like hello, the word hello,
Yeah.
it's taking the numerical value.
Ah, very good question. So how do you hash a string? Well, I've given you a hash function that does that. So what you do is you feed into the hash function the string, and it spits out a number. And that number can be like 120 million. But what you do is you mod that to your table size, and you go, boop, that's where it's supposed to be. So the function will do that for you. I'm not making you write that function. Yep, good question, though. Yeah. What else? We good? OK, I'd be happy to chat with people about the project. Just you have to email me or see me in office hours or whatever about that. Whew. OK. So this is it. Yeah, this is it. Boop. Well, there we go. All right. So as I said, the next thing we're going to talk about are some of these some of these data structures that we're to a point where they're more advanced than the data structures we started with. right? They're not your average, everyday types of data structures. But they use a lot of the concepts we've already done. Okay? And the first one we're going to talk about is this interesting idea called a skip list. Okay? And a skip list, well, we'll get into the details about that. But I'll tell you that it's related to a linked list. And this whole semester, what have I been telling you about linked lists? They're terrible. Right? That's what I've been telling you. Right? Linked lists are terrible. They're slow. And they've got issues to them, right? So let's say we had a linked list like this. 6, 12, 13, 45, and 72. Okay? And you've got a head pointer on here and whatever. Why do I say those are terrible? Yeah, Isabel. Yeah, if I want to find something, if I want to find where 45 is, I start here and I go, is that 45? No. Is that 45? No. Is that 45? Is that 45? Yes, finally. Okay, so what's the asymptotic complexity of that? Linear. It's terrible, right? That's one issue with it, right? Does it? Yeah, go ahead. Yeah.
I was going to say that like things aren't necessarily adjacent to each other in memory. So
Yeah, that.
if you're trying to access a lot of parts of it.
Yeah, it can be a little bit slower. It's definitely a memory hog and not good for caching and all that. But we're not going to worry too much about that aspect of it. The big aspect of it that we're going to care about is really this idea of, hey, it's really slow for doing searching, right? And the question is, can we make it better? Or for that matter, is there anything that we can do? Now, what have I already done to this? Yeah, it's already sorted. Does that help? Oh, it doesn't help? There's no way, there's no like binary search I can do on this, right? Because it's not adjacent and all the links go to, you don't have any access to like the third or fourth one. That's too bad. Okay, that's definitely too bad. Is there any way, if I allowed you to give me one other piece of information, could you make this better? Think about it for a second. If I said, give me one piece of information that would make my searching a little bit better, what could you give me?
The middle and the quarter.
What is it? The middle?
Like the
Oh.
middle and then like the quarter and the eighth.
Well, you only allowed one piece of information.
Take the middle.
Yeah. What if I said this was the middle? If I wanted to search for 45, what would I check first? I might check the middle and say what? If I know this is sorted, I would check the middle and say what? Is this bigger or smaller than the middle? And if it's smaller, what do? Go here. If it's bigger, I go where? Back to the start and go this way, right? Does that, in many cases, that would be a huge piece of information to know, at least to start me off, right? And then you said what?
How do you keep doing that? So then get another middle.
OK, so get a middle of a middle and a middle of a middle. I like that. OK, you're getting more information about this. Not a bad idea. OK, so we helped the list out. This is exactly what we're talking about, right? The halfway point does help. And then if you keep going with this idea, you might even do a little bit better, right? Hey, I have a question for you. See the order of this list? Anyone know what that represents? What is it? It is ascending. Sure, it's in order. But what order? Like, why did I put these numbers in that order? This class might not be big enough. So I'll tell you, I stole this idea from a lecturer at MIT who did a video that I watched, and it's such an awesome idea. I like stole it straight up. Okay, because it's awesome. I am on video saying this, but that's all right. If he hears it, he'll go, "Good. I'm glad he used my idea." I hope anyway. Fair use. I'll call fair use. But this number, I'll tell you right now, this is not a numerical sequence that happens in any kind of natural way. Well, that's kind of not true, but to the most part, that's not, like, it's nothing you would have necessarily known before. I'll give you a hint. Okay, I'll give you a hint. This range of numbers here, if you're a Boston Red Sox fan, you would probably hate somebody who would know what these numbers stand for. It's not the year the Yankees won the World Series, although that's a good. That's actually a good call. But it's not the Yankees. They would probably be a Yankees fan, but they would know about this sequence probably. Nope, not players. It doesn't have anything to do with baseball. It's just New Yorkers in general. Anybody from New York? The what? What about the subway? Anybody ever heard of a little movie they play next week on Thanksgiving all the time called Miracle on 34th Street? Right? Everybody heard of 42nd Street, which is in the middle of Times Square? What are these? Subway stops. Right? These are actually subway stops on the New York subway. And this is on the 7th Avenue line, if you've ever been in New York. And it's on the 7th Avenue line. But what's interesting about the New York subway is, so first of all, it's huge, right? It's gigantic. But second of all, anybody know what's unique about probably not unique, but special about the New York subway system in terms of the stops? Yeah. You have express lines. Exactly. Instead of having 2 train tracks, one going one way, one going the other, they have 4 train tracks. They have 2 going one way, 2 going the other way. And on one set of tracks, they have the local line, which goes to every stop. Bing, 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 bing. And they have an express line, which jumps ahead, because not as many people want to get on at 23rd. Although somebody in the other class today said, that's actually not true. 23rd is jammed with people because there's no express trains. And part of it is probably because they designed this in 1908 or whatever, right? And 23rd Street's, who knows, but back then, whatever. But you can see that if you want to go from 14th Street to, say, 59th Street, what do? You take the express from 14 to 42, get off the express, change lines, and go then to 59, right? Isn't this exactly the same idea as what we were talking about with making the linked list a little bit better, right? These stops represent the jumps that we could do to avoid doing all the ones in here. Okay? The bigger question, though, is where should we arrange these stops? We'll call this line 1 and this line 2. Where should we arrange the stops in line 2 so that if we didn't know anything about population and this wasn't like a social issue, where would we put the stops? That's the big question. What do you think? Al? Yeah, evenly spaced, right? We don't want 34 and 42 being right next to each other, right? Because we want to basically minimize our maximum search time, right? And spreading things out is important. Okay, so spreading things out is important. But what's kind of even more important, right? By the way, this is how you would get there this is not how you would tell somebody to get there. Well, unless you were a Red Sox fan, right? But if you were a Yankees fan, right, you would tell somebody to get to 59th Street by going 14, 34, get off of 42, change lines. In our case, we don't know that the next stop is greater than what we're looking for. So if we're going to 59, we have to go to 42. Then we have to check 72, and we go, oh, we went too far. And then we have to go back to 42 like that. You see how this search works? You have to do that, right? And if you're a Red Sox fan, you say, yeah, you want to go to 59th Street? Yeah, get off at, go up to 72nd Street, and you've gone too far. Then get back on, go the other way down to, and then you'd say lots of other bad words. But anyway, right? So, but that's how you're gonna do it in our case. Okay. All right. So equally spaced nodes is exactly what we want. I should have drawn the equally spaced nodes, but we wouldn't necessarily have a 42. We might have it a 50, and then we'd have a 66, and whatever. We'd spread them out as much as possible. Okay. Okay. The search cost is what we're trying to minimize here. Okay. Let me write this down. Okay. Let me write this down. The search cost is the number of lines in L1. That's what the little bracket means, right? Or the lines there. Plus the number of stops in this case, or links, in L2 divided by the number of stops in L1. Why? Because you basically have to, the worst case here, you might have to go through all of L1, and then only the portion of L1 that you have to go back like one stop, basically. You're dividing them all between. You have to go back to only like this ratio of the rest of the stops. OK, do you see how that works for as far as the thing? If we're looking at L2, which is this list, what do we normally call all the elements in the list? How many do we call it? N, right? So if we replace the number of stops here with n, right? If we want to minimize this search time, we're trying to figure out what n should be. Like basically, how many stops should we, or we want to, not what n should be, sorry, what this value should be when we add it together, such that how many stops we have up here versus the total we have. OK? We want to figure out what that ratio actually is. To minimize this, what kind of operation are we going to have to do? We have to do some calculus, don't we? Right? Let me rewrite this. I know you're like, oh my gosh, calculus. Right? Where's Cecily? She should be here for the calculus. She's calculus brain, right? Let me rewrite this like you might have seen it before. F of x equals x plus n divided by x. Can we minimize that? This is a pretty easy calculus problem, right? Pretty easy calculus problem. How do you minimize a function? Take the first derivative, right? F prime of x equals what? 1 plus. It's a little tricky. What is this rewritten as? No, well, you're close. Right? This is actually what? This is actually x to the negative 1 times n. Right? So what's the derivative of that? Negative n to the x negative 2. Right? OK, so we've taken the derivative. Once we take the derivative, in order to find the minimum, what do? Set it equal to 0. Right? We set it equal to 0, and then we just solve for x. Right? 1 equals nx to the negative 2. Right? So then we've got 1 over n equal, sorry, let's do it this way. Let's say, move the x squared, divide both sides by x to the negative 2. So we get 1 over x to the negative 2 is what? X squared equals n. So x equals square root of n. OK? It's pretty, that's a pretty simple derivation in calculus. And by the way, that's probably the only time you'll ever see calculus in a computer science class in your life. But there you go, OK? So what have we accomplished here? We've said, right, that L1 has to now be the square root of n. And the square root of n, can we simplify this? Can we simplify that? What is n divided by the square root of n? This is kind of, if you don't remember this is like clever once you think about it. 25 divided by 5 is 5. So isn't it just the square root of n? Right? N to the 1 divided by n to the 1/2 is n to the 1/2, right? So you've got square root of n plus the square root of n, which is just what? 2 times the square root of n, right? That's our search time. What it means, let me see if I did this on here. There we go. What it means is that if you have n nodes here, right, and up here you just have the square root of n nodes, and you space it such that these chunks are also the square root of n, then you've got the best case for the minimum amount of search time you're going to need. OK? OK, a little bit of derivation there for you. So that's what we've got now. We've got, OK, now we know that this has to be the square root of n node of this one. Can we do better than this? What could we do? What if this was 1 billion stops, and this was the square root of 1 billion stops? What could we do to this top list? Do it again. What if we just put another list up here, which is the square root of 1 billion nodes, right? And then the square root of 1 billion nodes, et cetera, all the way up to the top, right? We could do that, right? Could do that. Pay no attention to those little things. Those are artifacts of me being terrible at PowerPoint. But if we had more linked lists, so two sorted linked lists, we have a search time of 2 times the square root of n. Okay? By the way, we went from n to the square root of n. That's a pretty big improvement right there. Right? We've gone from having this horrible linked list, which is order n, to a linked list that's order 2 times the square root of n, which is pretty good. OK? Can't complain about that. But we can do better. What would it be if it's 2 sorted lists is 2 square root of n? What do you think 3 sorted lists would be? Any ideas? Cube root of n times what? 3. Right? 3 times the cube root of n would give you the asymptotic complexity of 3 lists. That's better. We're getting better. Right? How about for k lists? K times the kth root of n. Right? K times the kth root of n. OK? So let's see if we can think about what we really want this to be. Because how many lists are we going to want? What if we had n lists? Right? What if we had n lists here? What is the nth root of n? Any idea? The nth root of n happens to be 1, right? So then it would determine, if you had n lists, right, you would get an asymptotic complexity of n times 1, which is just n. So we don't want n lists, because then we're back to where we started, right? Which would be bad. We'd have n lists, and we'd have n time, and it would not be very good, right? There is an amount here that we actually want. It's a little tricky, but there is an amount that we actually want. Any idea what it is? Whoops, I just told you. Right? It's if you make the number of lists equal to the log of n, you get log of n times the log of nth root of n, right? And doing the math on this, the log of n times the log of nth root of n, you get 2 times the log of n. So we have now gone from order n, terrible, to what? Log n, which is awesome. What other kinds of things do we have that are log n? We have what? Yeah, how about trees, right? Binary search trees, right? All those heaps and things, those are all log n. Guess what this ends up looking like when you have log n lists? What does it kind of look like? Right? Kind of looks like a tree, doesn't it? It ends up being very tree-like, right? Because what you do here is you say, OK, there's this many. This is basically splitting the list, right, basically into 2 in this case. Then you split it again into 2, and you split it again into 2, and you split it again into 2. Right? And that's exactly what we do with a binary tree. We split it. We say, OK, this guy's children are like these 2 or whatever, right? And this guy's children are these 2. You see? So there's a very binary tree-like way to do this. OK? Questions on that? Kind of interesting how you do that. The big question, though, which we haven't even answered yet, which I think we'll get to next week. What's the big question? What haven't we? We've searched on that. We know how to search. How do I get to the 59th Street station? Where do I start? 14, and you go 14 to where? You go 14 over here, and you say, oh, went too far. Then you go back down to there, and 14. Then you go to here, right? And you go to 50, and 50's 50. You have to go to 79 again, and you go, oh, I got to go back here. 50. Then you go 50, and then you get to there. And what were we trying to find? 59, then you go back here and you go to 59. So it takes a little bit of time to get there, but you're still only traversing a logarithmic number of downward steps, right? So it's actually not too bad. Yeah, Alan? Yeah, you can make a graph of it. Really, it's a tree. I mean, it's more like a binary search tree in that sense, right? I guess you probably could make some sort of a graph out of it. Yeah, Denise? You do move from 50 to 50, yeah. You go from 50 to 50, you don't actually, I mean, you go to the next list and you look at the next one. So really, you're kind of going this way, right? I mean, you basically go down to this one and you look at the next one and see if it's the one you need. But I mean, if you wanted, you could probably have these go like that and save a little bit of traversal. But in terms of looking at it, it makes it a little nicer to look this way, right? You do have to duplicate a lot of things. Like you do duplicate a lot of these numbers. Like the 14 gets duplicated in every list, right? And the 34 gets duplicated in the next couple lists, right? 50 gets duplicated in 3 lists. So it's definitely it doesn't necessarily save a lot of space, but it works pretty well. But again, we've searched through this. What haven't we done? You wouldn't do this on well, you might do this on a subway. Yeah, they're doing this at Boston University. Actually, inserting new elements in here gets a little bit tricky. It's actually a probabilistic thing that you do. Like what you do, we'll go over it on next week, but what you do is, actually we'll go over it after break. Next week is going to be on Monday. Actually, I guess we could do it either way. We could do that Monday. At some point in the next couple weeks, I want to do a pre-Comp 40 like lecture on like what do you think you need to know for those of you who are going to Comp 40. For anybody who's not going to Comp 40, like if you're a brain science major or something, you're like, I'm done with computer science. You don't even have to come to class if you don't want to. Although I still think it's interesting. It's not like I'm gonna like talk about crazy stuff you'll never need to know. But some of it's interesting. But you don't have to come to class certainly. And it will not be testable. So maybe Monday's a good. Anybody gonna be out of town Monday already? No? Oh, okay. Well, then I guess I could do it Monday or Wednesday. So anyway, the point is that to do this, you have to do a probabilistic insertion, where basically you say, let's say I want to put it here. OK, what you do is you flip a coin, and you say, do I put another one up here or not? I mean, it's like there's a probability of doing that. So it's the first probabilistic data structure we'll talk about. Yeah?
Why do you need to create like new levels each time, and why not just like a point of finding 2 numbers?
Well, the easiest thing to do is to have each one of these be a list. It's the same idea, right? I mean, you're really doing the same thing. It's basically pointers. I mean, it's a linked list, but they're basically pointers. So it really is the same thing. Yeah, Jane?
So you're like making a whole new set of
Yeah.
okay.
Yeah. This is a list of itself. Then this is another list. This is another list. This is another list. And you just keep those lists. And by the way, this is actually easier to create than a balanced binary search tree, which is what you'd really want if you were doing a binary search tree. Right? So this is a pretty easy data structure to because you guys can create linked lists all day, right? That's not hard. And then you just duplicate them, and then you just have to do a little bit of math to figure out where all the other divisions are. So not too bad. But so why did I tell you about this thing? If you ever do like interviews for technical companies, if they ask you about various types of data structures, and you pull out a skip list out of your hat, they will hire you on the spot, right? I mean, I think from the standpoint of if you go, you know what, this is a good idea to use a skip list here, they'd go, whoa, this guy knows something, or this gal knows something, right? Because they recognize that this is something not many people know about. Okay? Any questions on that? I think that's about it. So we're not going to do this now. We'll start with this after we do a little more on the skip list next time. This thing called a Bloom filter. Questions on the project, on the movie tonight, which you should all go see. It's going to be right here. If you weren't here earlier. It's going to be right here. Whoops. Anybody else? Questions? What?
I was working on that all class, so I thought we were going to get to it.
Working on what? Bloom filters? What do you mean working on it all class? What are you doing in class? You should be working on skip lists. We'll do it next time. Sorry. All right, any other questions? I'll see you Monday, or in lab, or in whatever else.